Okay, just a warning here. Please forgive the speediness with which I'm going to go through these slides. This is now the third time giving this lecture. Hopefully this time it will actually record and keep it as it is. I'm going to end up dividing it up probably into at least two different versions in the hopes that it actually keeps recorded as opposed to deleting everything. So if you need to, make sure you pause it, slow it down, do whatever you need to. But like I said, I'm going to push through it pretty fast. When we look at our carbonyls, we've got our ketones and technically our aldehydes that we've got to be concerned about. Our general reactivity, if we look at the overall carbonyl functional group, is that our oxygen, being more electronegative with those lone pairs as well, more electronegative than the carbon, can take the electron density away, meaning that oxygen becomes an electron source. Electron sources, as you hopefully remember, can be a Lewis base, Bronsted-Lowry base, or even a nucleophile as a potential reaction. The carbon, having lost electrons, now wants electrons, so it can act as a Lewis acid or an electrophile. Can't really make it as a Bronsted acid because it doesn't have hydrogens. Okay, so when we think about the general reactivity, that's what you're supposed to be looking for those differences in electronegativity to generate those different functionalities. When we react with our carbonyls, we focused in on ultimately the reactivity of our carbon being that electrophile. So we looked at 3 and ultimately 4 different nucleophiles because we also have hydride coming in and reacting with this. We already looked at our carbonyl, our carbon reactivity and our nitrogen, so this lecture is going to focus primarily on our oxygen as a nucleophile, and we'll look briefly at hydrogen or hydride acting as our nucleophile. When we looked at nitrogen, we pretty much said that that was important because of the nitrogen carbonyl bond. Our nitrogen carbonyl bond being super important to biochemistry because that is a peptide bond in organic chemistry known as an amide. That functionality is really important because that generates how we link different amino acids with each other. Okay, so that was really important. When we get to our carbonyl our oxygen as a nucleophile, we generate new names that we can come up with. So if our oxygen source, I keep doing that. If our oxygen is coming from an alcohol, so we have our oxygen with some R group or carbons with a hydrogen on one end, or if our oxygen is coming from water, we get slightly different structures. Okay, if we've got our water coming or our oxygen nucleophile coming from water, we end up with something known as a hydrate. If it comes from an alcohol, that's where we get the acetal or hemiacetal, depending on how far through we go with that reaction. Okay. What you're going to be responsible for is identifying the carbonyl. So if you're given an acetal or hemiacetal, can you find the starting carbonyl that made that acetal and the alcohol that was necessary to react with it? Okay, so our alcohol being the nucleophile and our carbonyl being our electrophile. One of the last things that's important to realize is understanding the feasibility of the individual steps of the mechanism. Okay, so is it possible for a reaction to progress forward or not? Okay, so what happens is when we have our oxygen as a nucleophile, we have two possible circumstances that we can run it under. We can either do a base solution or base catalyst, or we can do acid catalyst. Okay, since we're looking at the acetal in this case, if we start with the alcohol and we run it under basic conditions, so let's say we add hydroxide, okay, a reasonably strong base, that base can pull off the hydrogen, and what we end up generating is a really good nucleophile in our now negatively charged alcohol. Okay, so that species can now act as our nucleophile and react. So under basic conditions, we generate a strong nucleophile. That nucleophile will react with our carbonyl, as we're showing in the upper left. So that electron density goes in and attacks the carbonyl, pushes it up. We generate a lone pair, or an extra lone pair on that oxygen, so it's negatively charged. That negative charge is going to want to get stabilized. We still have more alcohol in solution, so our negatively charged oxygen can now pick up another hydrogen and reform our catalyst, or sorry, our ethoxide, a new nucleophile that can then come in and potentially react. Our reaction temporarily, for the moment at least, would stop at what's known as the hemiacetal, because we're now halfway on the way to becoming a complete acetal. Okay, so to identify the hemiacetal, what we're looking at is we have two oxygens attached to one carbon. One of those oxygens has some carbon containing R group. The other oxygen is bound to a hydrogen. That's our hemiacetal. We still have an electrophilic carbon because we have that carbon with two oxygens bound to it. So given the right circumstances, we could now take our nucleophilic oxygen, another molecule of our nucleophilic oxygen, and that can now attack. Okay? In the process, we're going to want to kick out our leaving group, which in this case is OH minus. Okay? So if we look at our products, we would get our OH minus, and now we have officially our acetal. We've got our carbon that still has two oxygens bound to it, and now those oxygens, change the color a little bit here, now those oxygens are a little bit different from our hemiacetal because the oxygens are connected to two R groups. They aren't hydrogens. Okay, so that's our big difference on looking at where these things show up. As far as deciding is if this step of the reaction actually makes sense, is it feasible for it to occur? Well, one of the very first things that you guys noticed when we first talked about this is we have OH minus. Okay, it's kicked out of this. OH minus is a terrible leaving group. So how likely is it to have this actually occur? Well, not very likely. If we got a bad leaving group, we wouldn't expect our reaction to occur. The other thing that kind of suggests that this last step of the reaction isn't particularly likely is that we can go back and evaluate our reaction itself. What we're running is a substitution here, and what we can try and do is decide what mechanism it's running by. Well, based on where our arrows are shown, we're looking at happening all in one step, so we're looking at an SN2. Another thing that we could evaluate here is that our oxygen is negative, our nucleophile, so we have a strong nucleophile that again pushes SN2. Well, what are the odds that we could get the SN2 reaction actually occurring here? Not so good, because if we take a look at our substrate, this has two carbons attached to it, and it's sterically blocked by that other oxygen. So our sterics are pretty awful in this case, which would suggest this step of the mechanism is not a good one. Okay, so that's kind of the feasibility line that we run with. Well, if we still want to make the acetal, we're going to have to come up with another way to do it, and that's where we would shift to the acid-catalyzed reaction. So under acidic conditions, we would add a nice strong acid. Okay, in this case we've shown H3O+, but as we talked about in class, it's a bad idea because that introduces water, which is a nucleophile, and we don't want that. Whoops. So we could add just a strong acid like H2SO4. We don't need a lot of it, it's just there as a catalyst. The electrons from our oxygen can share with the hydrogen and push the electrons onto our sulfate. What this ends up resulting in is now an activated carbonyl. Oops, sorry. What we've got now is that oxygen doesn't want to be positive, so it can start to suck the electrons away from our carbon. That carbon now is positive and doesn't want to be positive, so it can suck some electrons up from our alcohol floating around in solution. The result is that we form that new bond between our alcohol and our carbonyl. We've broken, or we've put the pi bond now onto our oxygen. So it's picked up that lone pair. We formed the new bond between our alcohol and the carbonyl, and we've moved a step closer towards becoming a hemiacetal. You'll notice that we aren't quite there yet because our oxygen is positive, so what we'll do is take the electrons away from the hydrogen, put them on the oxygen. Sometimes it's nice to show where that hydrogen is going, so we can have another alcohol molecule come along and share its electrons with the hydrogen and help this reaction propagate forward. Okay, and what we end up with is our hemiacetal. Notice again the pairing in it. We've got a carbon atom that is bound to two oxygens. Those oxygens, one of them is connected to an R group, one of them is connected to a hydrogen. Okay, so there's our hemiacetal. If we want to continue to propagate towards our acetal, the hemiacetal is still reactive because of our carbon in the middle being near two electronegative elements, so it's still very partially positive. So what we can do now is evaluate that structure and say, okay, under acidic conditions, I want to try and get electrons somewhere. We don't want to have something come in right away because we still have a very bad leaving group. So what we're going to do is make that leaving group better by again going back to our acid, which again can't be H3O+. So we'll use sulfuric acid again. The lone pair electrons from our OH version can now pick up electrons and shuttle back across. Why do we not use our alcoholic oxygen? Okay, well that one's not valid because if we use those electrons to pick up the hydrogen, we go backwards. We go more towards the carbonyl than towards the acetal. Since we know we want to go towards the acetal, that's what we're going to work with. Okay, so it's one of the things that makes this chemistry a little bit more difficult. We get lots of possible reactions. We just have to do the one that's most likely to put us forward, okay, or put us where we want to be. At this point, we now have a phenomenal leaving group. So what we can do is have that leaving group leave. So what it will do is take the electrons away. Okay, our oxygen doesn't want to be positive, takes the electrons away, and we generate a carbocation. That carbocation is resonance stabilized from our other alcohol, our other oxygen, which means that it is relatively stabilized. So we've got a good leaving group, we've got a good stable carbocation, everything's good. We can now finalize our substitution and we can take the lone pair from another alcohol molecule, react with our carbonyl, and generate almost our full acetal. Again, we have one more step. We're going to want to deprotonate, so we'll take the hydrogen away from our oxygen, and put those electrons onto the oxygen. And we now end up with our acetal. Again, notice we've got our carbon with two oxygens bound to it, and those oxygens are then further bound out to R groups. Those R groups would be carbons. Okay, so that's our beginning to end. Kind of slow, at least as slow as we're going to see, for our acid-catalyzed acetal reaction. So we can see it now all put together in a single slide so you can see each step. One of the things that I want to kind of add to this slide before we move to the right would be adding what type of reaction occurred. Well, if we start at the very beginning, the only thing that happened was the transfer of a hydrogen. So we've got an acid-base reaction. When we move to the next step of the reaction, what's occurred? Well, this one's a little bit trickier, but we've got some kind of addition reaction. Okay, we've got the addition, okay, of our oxygen. We can kind of put this in quotes because it's a little bit odd. The addition of our alcoholic oxygen to our carbonyl. So we've lost that carbon-oxygen double bond. Okay, what happens in that next step? Well, it's another acid-base reaction. Okay, when we move down to the next step, yet again, another acid-base step. This one gets a little bit tricky. We get a leaving group leaving, okay, to make a carbocation. Okay, In the next step, we then had a nucleophilic attack, okay, to generate a product. What's the relationship between our step before we had that difficult organization? Well, if we compare the difference between those two, ultimately what we did was a substitution reaction. So when our leaving group left, we were actually looking at the first step of an SN1 mechanism. And when we moved to the nucleophilic attack, that could actually be better described as the second step of our SN1 reaction. Okay? And our very last step, what occurred, we just lost a hydrogen, we've got an acid-base reaction. Okay? So we can see all the individual pieces in there. And just because I always seem to forget and remember, we're going to go back to the very beginning and look a little bit closer at our first line to kind of evaluate what occurred. So we start at our alkene, or our carbonyl, and we move to our intermediate hemiacetal. Okay, not quite the hemiacetal. What changed? Well, we've got a hydrogen, and we have this group, and we've lost the double bond. So really, instead of saying acid-base right away, we could say this is the acid-base first step of an addition reaction. And the next step is the second step of our addition. So when we look at the acid-base, or the carbonyl reaction with a nucleophile, really what we've done is an addition-substitution reaction to make our acetal. Okay? So we can end up either coming up with new mechanistic names to explain the beginning to end, or we can go back to those same base 4 reactions that we looked at: addition, substitution, elimination, and acid-base chemistry, and refer to those. Okay? Last thing on this slide is a nice kind of summary, looking at the transition from our carbonyl all the way down to the acetal. Okay? Some things that we should point out is we can add an extra alcohol molecule here. So as we move from the carbonyl to the hemiacetal, what did we need? Well, we needed an alcohol molecule to react with it. When we move from the hemiacetal to the acetal, what did we need? We needed a second molecule of alcohol to react with it. And in the process, we end up giving up water. Well, what happens if I want to go the reverse direction? What do I need to add? Well, again, look at your reaction. We've got our acetal plus water takes us to the hemiacetal. How do we move from the hemiacetal to the carbonyl? We don't need anything actually for this. We could show, since it's in there, we could say that's part of it, and that can help facilitate the breaking of bonds. But ultimately, once we've started adding that water molecule in, it's going to push back to the carbonyl fairly readily on its own. Okay? So if we're going to try and reverse the reaction, all we've got to do is add water. Okay? And either make it an acid-catalyzed reaction or base. Either is fine. Okay? So, what can we do as far as identifying these? So what we want to identify or piece together, in all of these cases, our acetal, hemiacetal, or hydrate, we're looking for a carbon that is bound to an oxygen, or 2 oxygens. And in the case of the acetal, we've got R groups. In the case of the hemiacetal, our carbon is bound to those 2 oxygens, where one is now, instead of being an R group, one of those is now a hydrogen. When we move to the hydrate, instead of starting our reaction off with an alcohol, we started with water. Okay, so we'll still end up with a carbon. That's supposed to be an oxygen, with 2 oxygens bound to it. Except now, instead of that oxygen having carbons, it's going to have 2 hydrogens on either end. Okay, so what we're trying to do is ignore the rest of the structure and only look for these patterns. Once we've identified these patterns, we can decide what it is. So if we start at the far left, we'll go through. Here's our carbon. I see 2 oxygens bound to it. Okay, what are those 2 oxygens bound to? 2 carbons. Well, let's go through and try it this way. So we're looking at which pattern? An acetal. We move to the next one. There's our carbon with 2 oxygens bound to hydrogens. Which one do we have? We now have a hydrate. We move to the next one. We've got, whoops, come on now, our carbon bound to 2 oxygens. What's bound to those oxygens? Carbons. So we've got an acetal. We move to the next one, carbon with our oxygens. We've got a carbon bound to one of those oxygens, and we have a hydrogen bound to the other. So what we've got here would be the hemiacetal. And if we take a look at that last one, we would definitely have carbons and oxygens, but do any of our carbons, so if we call this our central carbon, yes, it's bound out to an oxygen, but then it's bound to another carbon. So that one can't be an acetal carbon. If we looked at it the other direction and said, okay, well maybe it's on the other one. Maybe this is our acetal carbon. Well, we've got our oxygen out, but then it's carbon and carbon. So again, no acetal. What does that mean? Acetal hydrate or hemiacetal. What does that mean? We would say not applicable. It's not going to be any of these. We're looking at some other kind of functionality here. We don't need to worry about it as far as this goes. The next level of difficulty to this is evaluating or identifying the carbonyl and the alcohols possible that come from this. Okay? So when we go through and run these individual reactions, what we're going to end up doing is identifying our carbon that has the 2 oxygens bound to it, and we're going to draw out the end result, our starting material from that. That carbon is still going to have 2 oxygen bonds, but it'll be to the same oxygen. So ultimately the bonds we're breaking are those. Okay, so if we break that off, we also have 1 oxygen, our second oxygen, and if we count out the rest of the bonds, we end up with both of those. If we were under base catalysis, we could put a negative charge there. Okay, what catalyst are we under? Well, it doesn't really say, but the problem does say identify the alcohol. Are these negatively charged species alcohols? No. To be an alcohol, they must have hydrogen. So there we go. We now have our carbonyl and our alcohol that came from this. An acceptable answer would be just to include one of them. Okay, why? Because in an actual environment and in actual chemistry, we would have tons of that alcohol floating around, which would mean there's more than enough to react with it to push all the way to the acetal. We don't need to specify that there's a second equivalent of it. Okay? If we were going to try and draw the carbonyl from our hydrate, what color did I pick for that? We'll do the same general idea. We'll identify our carbon. That carbon needs to have our double bond to an oxygen, and then the rest of the structure follows. There's our carbonyl. That reacted with, ultimately, HO, so our R group, if you will, in this case was an H. To make it an alcohol, again, in quotes, we could add an H there. So ultimately we reacted carbonyl with water, hence hydrate. Okay? We shift to the next one, which I would say is even more or a little bit trickier. Again, we want to identify our carbonyl. Okay? Look for that carbon. That's going to be the most important one. So we'll start there and say that is where our carbonyl was. Okay? We could even add in the oxygens if we like. And what we'll try and do is maintain their relative position so we don't shift anything around. Okay? Go back to our carbonyl. We know our carbonyl is connected up to 1 carbon, connected out to another, to another, to another, and then back to the oxygen. So there we go. That original carbon here is also connected out the other direction, which means we should show that. Okay? It needs to be an alcohol, so did I put too many carbons? 1, 2, 3, 1, 2, 3, 4, Yeah, I did too many carbons on that side. Try that again. I got to a carbon, one more, there. Still looks a little bit weird. Hopefully that's okay. At least you get the idea, hopefully. Again, we need it to be alcohols. So what's the result here? Our alcohols happen to be in the same compound that had the carbonyl. So it's a little bit funky, but that's fine. It doesn't have to be separated from it, and that's really what makes this one tricky. What type of carbonyl did we react here? Well, we've got our carbon here, fourth bond out to a hydrogen. We're looking at an aldehyde. Okay, so that aldehyde with our two alcohols could come through and make that out. For our very last one to evaluate, we've got the hemiacetal. Again, focus in on that carbon. We want the double bond oxygen. Draw in our other CH3s. We add our alcohol with another CH3 on it. Make it an alcohol. There we go. There's the alcohol starting material. For the one that's not applicable, it wasn't an acetal or any of these, so it doesn't make sense to try and draw where it came from. So we can't look at the carbonyl or the alcohol, so we won't evaluate that. Okay. The next two are a bit more challenging, particularly because I'm about to delete a bunch of information, but you should be able to go through and do the same idea with these. Both of these are acetals, so I'm going to go through and solve these pretty fast. We'll identify our carbon that has our two oxygens attached to it. So we want to put in our carbonyl. The new bonds are out here, so the rest of this is all the same. So we need to draw that in. There we go. Okay. If we add in our other oxygens to try and maintain the geometry, what we end up finding out is that we're reacting now, instead of three things or even just one thing, we get two things. Our alcohol happens to be a diol. It has two alcohols in one molecule. Okay, probably one of the more common uses for our acetals. When that reaction occurs, when we go to make our acetal, what we've done is protected the carbonyl. Because this chemistry is easily reversible, I can go through and convert the carbonyl over into something that won't react as an alkene, because we don't have, or react as a carbon-oxygen double bond. So I could now go through, if I had, say, another double bond in here, now I could reduce the reaction with, say, hydrogen in the acetal form, because the carbonyl isn't there to react with hydrogen. So I could reduce that away. So that's one of our more common applications when we look at our acetals. Last one, identify our carbon. This one's going to look kind of goofy, but we want to draw in our carbonyl. So there's our carbon-oxygen double bond. Propagate outwards from that. And we can kind of just star around as we go. As we move slowly, we're just kind of trying to trace out the rest of it. Bound to an oxygen, bound to an oxygen. That oxygen must be different, so we've got an extra bond there. And we can make it an alcohol. Very similar to, I believe it was the middle one from our last set of examples, except now we have actually a ketone, not an aldehyde. So our alcohol and our carbonyl source came from the exact same molecule. It was all within one thing. So what we've got is an intramolecular acetal formation, okay, or an acetal reaction, because it happened within the same molecule. Okay. Last thing to talk about before I'm about to stop this and move into the arenes, I think, is we've got the reduction and oxidation reactions. Okay, there are actually several reduction reagents that we could potentially use with our carbonyls. I'm only going to have you be responsible for two. Okay, the old one that you've already seen before was looking at H2 with palladium, platinum, or nickel. When we do that reaction, H2 is not specific. It reacts with all double bonds. So if we have a carbon-carbon double bond, reduce it. If we have a carbon-oxygen double bond, reduce it. Carbon-nitrogen double bond, guess what? Reduce it. Okay? So what we want is to get something that's a little bit less reactive, so it's very specific. So one of the reagents that we can use is something known as sodium borohydride. This is a selective reagent in that it will only react with our carbon-oxygen double bond, in particular aldehydes and ketones. Okay? How does it end up working? Well, if we draw out the Lewis structure, we get this guy. Boron, if you remember, is a special molecule. It only really needs 3 groups of electrons, which means one pair of electrons, or one of those bonds, is actually really chilling on the nitrogen, not on the boron, even though we call the boron negative. Which means that our sodium borohydride can actually act as a hydride donor, and it can give up a hydrogen nucleophile. Okay? So we end up generating H- as a nucleophile. We've seen H- before in sodium hydride. Sodium didn't stabilize the hydrogen well enough to allow it to act as a nucleophile. Sodium borohydride has slightly different chemistry that allows this reaction to actually occur. If for some reason you're really interested in it, you can press me about it after the exam, because I'm not going to ask for much more than this. That you know that you can use sodium borohydride to reduce the carbonyl and not alkenes. Okay? As far as the oxidation reactions go, we're not talking about anything new here. All that we're really going to say, or all I'm going to say, is that your ketones, we can't oxidize any further. Your aldehydes are possible to oxidize down to the acids when using the proper oxidizing agent. We've looked at 2 of them, PCC and chromic acid. Which one will oxidize to the acid? The one, well, we could memorize this as the one that sounds like an acid. Chromic acid, being the really strong oxidizing agent, will push aldehydes all the way to the acid. If we add them to a ketone, nothing happens. Okay? The other memorization device that we talked about in class, PCC is ultimately another form of chromic acid, but it's politically correct chromic acid, so it's not quite as harsh. It will not react with aldehydes. So when we're looking at our oxidation reactions with carbonyls, really the only one that works, chromic acid. PCC won't do it. Okay? So let's see. Did I actually remember this right? There's some extra space that we could draw sodium borohydride, and we don't need to worry about that. Last thing I forgot, our ketoenol tautomerization. Turns out carbonyls actually have some extra chemistry associated with them. That extra chemistry has to do with the hydrogen on the carbon next to our carbonyl. Okay? This hydrogen ends up being relatively partially positive, which means it can act as an acid, which seems a bit odd. We don't expect a hydrogen attached to a carbon to be particularly acidic. So why would it be acidic? Well, we can take these electrons away and put them on the carbon, and what we generate is this species with a negative charge on that carbon. Well, carbon really can't hold a negative charge well, so it can then find some place to share them. We can shift the electrons, sorry that's an awful lot of blue, we can shift the electrons into a pi bond, but then that means this next carbon has too many electrons. So we take the pi electrons in that bond and shift them upwards. The result is that first off we've drawn a resonance structure, and our oxygen is now negatively charged, and we have a double bond here. Well, oxygen doesn't want to be negative, so what does it do? Shares its electrons with H+, and we make what's known as the enol. En, because it's got a double bond, or an alkene, and then we have the ol part because we have an alcohol. This process is known as the ketoenol tautomerization. Keto, because you're starting ultimately at a ketone, though it could be an aldehyde, and you're ending at an enol. Okay, no idea where tautomerization comes from. You can look up the Greek, Latin, German, whatever you want, roots, and figure out where that came from. Okay, I just want you to be aware that this chemistry does occur, and it does happen. I wouldn't say, because I don't remember exactly, with that much frequency in biochemistry, but I'm pretty sure there's a few reactions that you do get this ketoenol tautomerization popping up in different reactions that you might see in biochemistry. Okay, so it's one of the reasons why we've got to at least address that chemistry is there. To top it off, what makes this more interesting or applicable is that ends up generating a pretty nucleophilic carbon. Okay, because that carbon, if we go back to our resonance, is negatively charged. Okay, so our ketoenol tautomerization, it's a fairly rare process. It prefers to stay as the carbonyl than as the enol, so it doesn't happen. We don't shift the enol all that frequently, but in biochemistry there are enzymes that help push that chemistry towards that direction. Okay. Okay, so let's see. Last slide. Good. So I'm going to go ahead and stop here because it's recorded.